are still coming in, I'll just say welcome to everyone. Welcome back to the fall semester. This is our physics colloquia series. They're supposed to have coffee, so don't be turned off like there was a hiccup today. We'll make sure next time there's coffee. I hope the speaker has some chance to get some coffee today and is not like about to fall asleep. Welcome all. I, as a chair of the colloquium committee, I'm not going to take a lot of time. I just want to say this is a whole series of events for those who are attending for the first time. We've already got about 14 speakers confirmed, a few more slots to fill for the whole academic year. Throughout the US and some national labs like Lawrence Livermore National Lab, CERN from Geneva, we have a speaker, SLAC, National High Magnetic Field Lab, Dark Energy Spectroscopic Instrument Collaboration. We're going to have an update in Harvard Center for Astrophysics, Harvard Smithsonian. So you'll see there's quite a breadth of speakers. And so without further ado, I'll have my colleague Stefan Alexander introduce today's speaker. Thank you for coming.
Thank you, Matthias. It was a real pleasure that our first speaker is actually one of my favorite cosmologists. And you might wonder, how could this be the case? Well, in about 2 weeks from now, me and my two graduate students, Max. Mike was my former graduate student. Mike is actually here. Where's Mike? Mike graduated a couple of years. He's a happily postdoc at MIT, and hopefully he'll get a job next year. I'm just kidding. He will get a job. Anyway, so Max and Jake, we're putting a paper out on something to do with quantum cosmology. And when I was a postdoc at Stanford, my advisor, Michael Peskin, said, I see you interested. And he pulled out a PhD dissertation written by, and he goes, yeah, this student of mine, he loved special functions, and it was on stuff that we're working on currently. And it was a PhD dissertation of Bharat Ratra, who is our guest today. So I get very familiar with your dissertation back then. And I ran away from special functions very quickly after that. But we overlapped again because he did groundbreaking work with Nobel laureate Jim Peoples. And I'm sure he's going to talk about this, having to do with dynamical dark energy. And Bharat did his PhD at Princeton and then went over to do postdocs at Stanford and Caltech and other places, and then landed a faculty job at Kansas. And we're really pleased that you're here. Thank you so much.
Hello. I guess it's on. So hopefully everybody can hear me. Thank you very, very much for that very kind introduction, Stefan. So besides my mom, I know somebody else has read my thesis now. So before I start, I just want to point you to this website here, and it's got some really, really nice videos about global warming that are really clear. And this might be something you want to show people. And it's going to be important. So I'm a cosmologist, and it's a really exciting time to be doing cosmology. Everybody's seen the great photographs from the James Webb, and you're getting a lot of really great data that are coming in and reinforcing two extremely striking results. So one is that we don't understand 95% of the energy budget of the present universe. And the other one, if it holds up, is that these observations are suggesting that either quantum mechanics or relativity or both are incomplete. And if that holds up, that's going to be really profound, because quantum mechanics and relativity have been the foundations for a lot of physics for over a century. So I'm going to talk a little bit about dark energy, but I'm going to have an introductory part, and I'll start with the current energy budget. So we know about 5% of it is baryonic matter. That's the name cosmologists give to atoms and molecules and blue whales and elephants and things like that. And this number was pinned down through the work of Gamov and his postdoc and graduate student, Alpha, and his postdoc Herman. They were trying to generate the light elements, and they realized that there'd be photons left over. Through a very inspired guess, they decided that they would be in the microwave part of the background radiation. And it took a long time, but eventually Penzias and Wilson at Bell Labs discovered those, and that explanation of their experiment was provided by the companion paper of Dickey, Peebles, Rowland Wilkinson. So even before that, in the 1930s, this guy was looking at clusters of galaxies, and he could measure how fast these galaxies were in orbit around each other. And he assumed that they were, this motion was produced by gravitational fields. And he could figure out from the velocities the amount of mass he would need to produce those gravitational fields. And he realized that that mass couldn't be in the shiny stuff. It wasn't in the stars. It wasn't in the hot gas. And that was the first indication of dark matter. There's got to be matter out there. There's got to be mass out there that's not absorbing or emitting light. And Zwicky could measure how fast these guys were moving, and they were moving at hundreds to thousands of kilometers a second. So that's non-relativistic or cold motion. And it's not made up of baryons, but that took another 30 or 40 years to establish while this number was getting pinned down. And Rubin's work was really important for that when she was looking at galaxy rotation curves. And even more recently, people have discovered something stranger, which they call dark energy. It's dark because it does not absorb or emit light to the extent that ordinary atoms and molecules do. And this choice of this name, energy, comes a little bit unfortunate. It's not energy in the sense of mechanical or chemical or electrical energy. It's just a name to distinguish it from that matter up there, which was found earlier. And if this is made up of particles, these particles are going to be very, very light, and they're going to be moving at the speeds close to the speed of light. So it's relativistic, and it's also non-baryonic. And it's the biggest contributor to the current energy budget. So we only know about these two guys through their gravitational effects, and we don't know anything else about them. And I had a very, very nice lunch with the chairperson today, and I've had a really nice visit talking to people, but it's really nice, and she's a very wise chairwoman, a chairperson, and I'm sure she realizes that for every person in the physics department studying atoms and molecules, you need 19 people doing cosmology. So this is an outline. So I want to motivate dark energy, and then I'll look at two dark energy models. There's a standard one where dark energy is a cosmological constant, and then there's the model ϕCDM where you turn it into a dynamical field, a scalar field. And this is a pretty messy model to work with. So people who want to talk about dynamical dark energy have used simpler parameterizations. There's the WCDM or the XCDM parameterization, and DESI has made this one pretty popular right now, and I'll talk about both of those. And so what we're going to do is we're going to make predictions from these models, and these predictions are model dependent, and you can then compare them to observations and get constraints on the model parameters, and you can compare different data set constraints and see whether they're consistent or not. And I'll try to look a little bit at the deceleration-acceleration transition. So earlier on, ordinary matter and dark matter dominated and decelerated the expansion, and then dark energy kicked in and caused this acceleration. And I'll try to talk a little bit about measurements of the Hubble constant, measurements about space curvature, and a little bit about the excess CMB weak lensing that seems to be present in the Planck PR3 data, and then some of the DESI recent results about dynamical dark energy. So we are dealing with very, very good data right now compared to previous times, but this data is not as good as, say, particle physics data from the LHC at CERN. So you can't draw any model-independent conclusions. And the way you want to use this data is you want to use physically motivated models that have maybe 4 or 5 or 6 or 7 parameters, and try to use these measurements to constrain those parameters. And then you can do a lot of things when you get these constraints. You can compare constraints from different data sets, and if they don't agree, then you either have a systematic error you're missing in one of the data sets, or the model you're using to analyze those data sets are inconsistent and can be discarded and ruled out. And you can use these models to combine constraints from different data sets on these parameters and get tighter constraints. So we have Hubble's law. where the recession velocity of the galaxies is proportional to their distance from us. And this constant of proportionality is the Hubble constant. It's got dimensions of 1 over time. But astronomers measure velocities in kilometers a second and distances in megaparsecs. And so it's got units of kilometers per second per megaparsec. And my favorite value is around 68. Excuse me. So this law holds at all times. You can go back to earlier times at higher redshifts, and the constant of proportionality will be different. And so that guy, when you talk about it as a function of redshift, is called the Hubble parameter. And the current value of the Hubble parameter is the Hubble constant. And this is an illustration of the data that supports this law. This is from a very famous paper written by Wendy Friedman, who was the lead investigator on one of the key projects for which the Hubble Space Telescope was built. And you're looking at the recession velocity here against the distances these galaxies are at. And you can ignore the residuals here. So at 100 megaparsecs away, it's moving at about 7,000 kilometers a second and so on. And this is the best fit law value. The slope was 72 kilometers per second per megaparsec in 2001. And since then, we've worked on trying to measure the Hubble constant also. And we've collected a lot of these measurements from a website that was run by John Hukra at Harvard-Smithsonian. And in 2001, we wrote a paper, and we realized that the Hubble constant error bars were so tight that the Hubble constant distribution of these 270 measurements we were looking at was non-Gaussian. And so you can't analyze non-Gaussian data that easily. And so what we did is we invented a median statistics technique. And when we used that for 553 Hubble constant measurements in 2011, we ended up with this number, 68 plus or minus 2.8. And this includes all the systematic errors because you have enough measurements from different techniques, like from surface brightness fluctuations from supernovae, that you can analyze them separately. And the scatter and the Hubble constants you get from those different techniques give you the systematic errors. And this is agreed with pretty much every measurement since then. And there's a slight issue with differences between Hubble constant measurements. So some groups get a higher value, and this is again from 2011. So this group was getting about 74, and I'm going to look at 68 also. And what I'm going to do here is I'm going to analyze data from the CMB on large scales and on smaller angular scales, and from galaxy clustering from the Sloan survey. And I'm going to use the standard ΛCDM model, but what I'm going to do is I'm going to extend it by allowing more relativistic or less relativistic degrees of freedom parameterized by n effective. And I'm going to marginalize over everything while using these two guys as priors. And you can see what happens. The blue contours come from this 68 value, and the red ones come from 74. And in the standard model of particle physics, we know that there are three relativistic neutrino species, light massless ones. And that's consistent at better than 1 sigma with the 68, and it's about 2 sigma away from the red ones at 74. So in 2011 or 2012, the standard model of particle physics favored 68 over 74 if you believe the standard model of particle physics was complete. And that's pretty striking because 15 years before that, you didn't know the Hubble constant to even within a factor of 2. But, I mean, this is one issue that's got to be resolved, whether this is the correct one or this is the correct one. And so we have an expanding universe. That's what Hubble's law tells us. And then we've got to remember that there's privileged observers when you have something, an expanding universe. So you can think about an observer in a rocket ship that's moving relative to the expansion, and that observer is going to see a Doppler effect, and the universe won't necessarily look isotropic to that observer. And it's only to the observers that are at rest with respect to the expansion that it looks isotropic. And then you postulate this cosmological principle that every observer will see an isotropic distribution no matter where he or she is in the universe, provided she's at rest with respect to the expansion. And this, from geometry, then implies homogeneity, which makes our life much simpler in theoretical cosmology, because once you ignore the global topology, you just get the three simple Friedman models. So you get, I can't draw the three-dimensional spaces. We live in a three-dimensional space here, and that would be the analog of the flat geometry. It's got to go out to infinity in both dimensions. And for those of you who know some GR, the line element's up here, and the scale factor for the curvature part is here. And for the flat case, the curvature is 0, spatial curvature is 0. And this parameter measures the density of matter in special units, and I'll come back to that in a second. All you've got to know is that this is equal to 1 for the flat case, and it's underdense for the open case where the curvature is negative, and it's overdense for the closed case where the curvature is positive. So we can kind of loosely think of this time part of the scale factor as the radius of the sphere, and as time goes on, it gets bigger and bigger, and that's our dynamical variable. And we want to write down equations of motion, and if you think of a harmonic oscillator, the dynamical variable is just the x, the displacement from equilibrium, and you can go with mx double dot equal to minus kx if you have a Hooke's law force. And you can also integrate that and get the energy equation, which is 1/2 x dot squared plus 1/2 kx squared equal to a constant. And that's what I'm going to write down here for cosmology. I'm going to write down the energy equation. So the dot is the time derivative, a is the scale factor, and this is the energy in the expansion. And it's being driven by gravity, and that's why we get Newton's big G over here. And I don't want to talk about the whole universe. I'm going to look at it locally and see how it affects space locally. So I want to look at the energy density or the mass density. So that's why I've got rho here. And the curvature of space can contribute to this also, and a cosmological constant. So unlike the harmonic oscillator, where you can integrate that 1/2 mx dot squared plus 1/2 kx squared equation equal to a constant equation, you can't do that here because the universe is expanding and the density drops and it's a function of time. So you need to figure out that time dependence, and that just comes from this expansion doing PDV work, and I'm working in natural units, so you don't see the c squared in the denominator. But the rate of change of the energy density, the rho dot, is equal to minus 3 a dot over a rho plus p. And to complete the set of equations, you need an equation of state that gives you the pressure in terms of the energy density. And once you have that, you've got all the equations you need. This is the only assumption you're making here is it's an ideal fluid model, and you're looking at just the homogeneous part, but you can generalize this as you need to. And the expansion rate is a dot over a, and that's the Hubble parameter. And we're physicists, so we might be able to figure out how to differentiate things, at least, if we can't integrate. And so one thing you can try to figure out is the increase or decrease in time with this guy. And you can get the relevant equation really easily by differentiating this equation and doing a bit of calculus to get something in this form, which is pretty much equivalent to a equal to f over m. The double dots being the acceleration of the expansion, and it's being driven by gravity, so we have the g here. Curvature doesn't show up in the second time derivative equation, but you get rho plus pressure, and this is matter, ordinary matter, and dark matter, and that 3 comes because the pressure, there's 3 space dimensions for the pressure, and if I wasn't working in natural units, that would be divided by c squared. And so you can immediately, if you ignore the cosmological constant, you know that energy density and pressure of ordinary matter is positive, so you predict deceleration. And that's a problem because astronomers find accelerated expansion now. So you patch it up by putting in a rho plus 3p lambda, and choose the equation of state to be of this form, then rho lambda plus 3p lambda is minus 2 rho lambda, and you make rho lambda bigger than rho matter and overwhelm this. And so you flip this sign and you get accelerated expansion. And I mentioned this parameter omega earlier, and that's just the critical energy density, the ordinary energy density divided by the critical energy density. And the critical energy density is got when you drop this guy and drop this guy, and rho is completely determined in terms of g and the Hubble constant. And this is the fudge factor in the Hubble constant. So instead of carrying around so many powers of 10, we just talk about the ratios, and omega is of order 1. So dark energy, the way it was discovered is you look, this is a cartoon explanation. You look at Hubble's law in two different models, one that's more slowly expanding, one that's more rapidly expanding. And as you go back further in distance, you're going out back further in time. And so you had three options. The expansion rate could have stayed constant. It could have sped up as it came in. It went like the blue one here, or it could have slowed down. And in the 1990s, the objects to which you could see the furthest with were the type 1a supernovae. So they were all pretty much in the blue part of the diagram. And so you got accelerated expansion. And then you could get these plots that showed you the likelihood as a function of dark energy in form of cosmological constant and ordinary and cold dark matter. And if there was no dark energy, it would be over here, but it was up here about 3 sigma away from 0 lambda. So now it's about 5 sigma away just from the supernovae data. So we know there's dark energy, and we know it's the major contributor to the energy budget, but we don't know whether it's independent of time and independent of space, or whether it varies with space and time. And the easy way to study this is to make models where it's time dependent and then see if they fit the data better. And you're making a whole bunch of implicit assumptions, which I think are fairly reasonable when you do this. And so I'm going to look a little bit at models, and this is the standard one. This is the ΛCDM one. And we have the Friedmann equation here. And I'm not going to go back to the time when radiation was important. So we're looking at late times. This is a scale factor here, and the energy density, and it's a log scale. And so this is ordinary matter, and it drops like 1 over a cubed, and it's the B line, blue line. And up here it dominates, so you get decelerated expansion. Then curvature kicks in, and then the cosmological constant kicks in, and then you get accelerated expansion. And the problem here is somewhat obvious with the cosmological constant. This is energy per unit volume. So you can go to natural units, and it's energy to the 4th power over here. And if you take the 4th root of that, it tells you the energy scale, which is roughly 1/10 of an MeV. And in the 1990s, when people discovered this, they didn't have anything happening at 1/10 of an MeV, and that disturbed people quite a lot, that you're having a fundamental energy scale so low in energy. And so one way to resolve that is to make this line tilted a little bit, and then you can go back to very, very early times where the fundamental energy scale is GeV or TeV or much larger. And then because the universe is old, you can drop that down to 1/10 of an MeV now. And one example of that is this W or XCDM parameterization. I'm making it spatially flat and simplifying it. And the Friedmann equation is the matter, the cold dark matter, and the baryonic matter. It's the blue line. And this guy is the green line. And that's our dynamical dark energy. It's got an equation of state in this form. And if W sub x is less than minus 1/3, it'll give you accelerated expansion. And the problem with this is pretty obvious, that if you take dp d rho, that's going to be negative, and that's the speed of sound squared in this material. And that's going to give you unstable, rapidly growing inhomogeneities. And so this cannot describe the real universe. And the way people deal with this is they just pretend CS squared is 1, that it's going at the speed of light. So one way to deal with this physically is to turn this into a physical substance, a scalar field with the potential energy density. And so the energy in that scalar field has a kinetic piece plus a potential energy density piece. And I've chosen this potential as an inverse power law because it's got some really nice attractor solution properties. And so you have that contributing, and that's the green line over here, and the blue line is the ordinary matter and the cold dark matter. And this has got an attractor such that the dark energy, the scalar field energy density, wants to always come to dominate whatever the dominant energy is here. In this case, it's matter, and it wants to take over. And so this can partially explain why we have this coincidence now that the cosmological constant and dark matter and ordinary matter have roughly the same omegas, and that's because this is kicking in now. So what we're going to do is we're going to take these guys, and I'm going to show you some older work because the error bars were much bigger and you can see the contours more explicitly. And we're going to constrain all these models with these illustrative data sets. And the precise data sets are not that important, but I want to show you what the contours do. And so what we do is we take everything in terms of the redshift, and this is the Friedman equation for the lambda CDM model written in terms of redshift instead of scale factor. And that's the omega matter contribution, omega curvature, and omega lambda. And you can see that if you look at this at the present time and set that equal to h naught squared and z equal to 0, you get a sum rule over here. So even though there appears to be 3 parameters in this model, only 2 of them are independent. And conventionally, these are the 2 guys that are taken when you're parameterizing this model, omega matter at the present time and omega lambda. And since omega lambda doesn't have a z contribution, you don't have to specify what time you're evaluating that at. And so the expansion rate depends on redshift, it depends on the cosmological parameters, it also depends on h naught, and it depends on this function e, that's a function of z and p, and that's just the square root of this guy. And so you take this and you make a prediction for the expansion rate or the Hubble parameter at whatever value of z you measure it, and then you compare to the observations, and you can do maximum likelihood, or you can do least squares or whatever you want, and then derive the likelihoods and then project them down on these planes. And so I'll have 3 of these plots here. So this is going to be a lambda CDM, that's going to be x CDM, that's going to be phi CDM. Excuse me. On this axis, we have omega matter. Over here, for lambda CDM, we have omega lambda. This is W sub x, the equation of state parameter in the x CDM model. And this is alpha, the power law index for the scalar field potential energy density. So there's a dashed line over here and a dashed line over here. And this dashed line divides you between closed models and flat models, so that's zero curvature. This dashed line is at W sub x equal to -1, so that equation of state for W sub x then becomes P equal to minus rho, which is just lambda CDM. So this is a flat lambda CDM set of models over here. And at alpha equal to 0, you also get the flat lambda CDM models here. So any model at a value of, say, omega of 0.2 that's either here or here or here is the same model. And that as you move away this way, you increasing or decrease, changing your curvature. And as you move away this way, you're going to dynamical dark energy. And as you go up here, you're going to dynamical dark energy. And then you see these lines that are dividing you from currently accelerated expansion versus currently decelerated, and you can see them in each of these plots. So the first thing you see is that you have 3 sigma contours, 1 sigma, 2 sigma, 3 sigma, 1 sigma, 2 sigma, 3 sigma, and you have best fit points from these data. And this is type 1a data from 10 years ago. of 12, 13 years ago. And you can see that most of the likelihood is in the accelerated part of parameter space. So no matter what model you use to analyze these data, you get accelerated expansion. And the best fit models are completely consistent with the standard model, no matter what model you use for the expansion, for the analysis. But there's lots of room for space curvature, lots of room for dark energy dynamics. So we can look at older BAO data, and you get the same sort of plots, but the big difference is that the contours are rotated. So if we look at the ΛCDM ones, the contours line this way, and you compare that to the supernovae ones, they go this way. And you can immediately see the huge advantage you get by combining different data sets and analyzing them jointly. But other than that, again, the accelerated part is much favored, and the standard model is very consistent with these data, and there's lots of room for space curvature or dark energy dynamics. And you get the same thing when you're looking at the expansion rate or Hubble parameter data. And here, because the Hubble constant is one of the points, and there's this big difference between these two Hubble constant values, I'm showing you two contours. The solid lines are for 68, and the dashed lines, dot dashed lines, are for 74. But they only move about half a sigma. And again, you draw the same conclusions. And you can see this from growth factor. So the conclusions you get from this is that the different data sets give you constraints that are not inconsistent. So maybe we're not doing something crazy because you're coming to the same conclusion from each of these data sets, although the conclusions are not that restrictive. And the individual data sets are quite consistent with the standard model, ΛCDM, omega lambda of 0.7, omega matter of 0.3. But there's lots of room for dynamical dark energy and spatial curvature. And so the next obvious thing to do is do this two at a time. And you can see that you're restricted to a smaller part of parameter space. The standard model is quite consistent, and there's room still for some dark energy, space curvature and dark energy dynamics, but less than what was previously available to single data sets. And you can look at two data sets at a time and draw the same conclusions. And you can see that there are systematic effects. So they give you tighter constraints when you combine them two at a time, and the standard model is quite consistent with these constraints, and you have space for dynamical dark energy and space for space curvature. But we're also starting to see that there's systematic effects, and so the value of the Hubble constant can change things. And I didn't show you the different supernovae data sets, and they can move things by half a sigma. And there's a lot of systematic effects. And I'm going to come back to the most recent data soon and show you those constraints. But I'm going to change gears a little bit and look at this deceleration-acceleration transition. And this also is from 10 years ago. And we're looking at 28 independent measurements that are over redshift from almost 0 to about 2.3. And these are the measurements. And what we're plotting here is the Hubble parameter divided by 1 plus z. So the baby universe is this way, and we live over here. And these are the 6 best fit models that fit these data the best. And there's 6 of them because there's 2 different values of the Hubble constant. You can see there's 3 here and there's 3 here. So one's 74 and the other's 68. And then you have ΛCDM, XCDM, and phi-CDM. And these are the 2 3 sigma deviant models that don't fit these data points that well. And this is very noisy data, but it's pretty dense in redshift, so we can bin these. And if I do that, the thing becomes a little bit clearer. So we can't bin these data points over here because they're at high redshift and they're very sparse, and we start binning them. It won't be clear what redshift to put them at, and so I'll leave those there. And so these are the individual unbinned measurements, and these are the bin measurements. And you can kind of see that there's a slope here and a dip, and you get the acceleration. So if you're looking at this in terms of the lambda CDM model, at low redshift, this is going to be the dominant term, and the cosmological constant is giving you the accelerated expansion. At high redshift, the matter contributes the most, and that's giving you the decelerated expansion. So we can see the transition from dark matter domination to cosmological constant domination. And this transition redshift was about 0.75 or so, and these error bars probably are a little bit larger now because we have a better handle on systematic errors. Okay, so I want to make another transition now, and I'm going to look at the most recent non-CMB low redshift data, except I'm going to exclude the DESI data, and I want to measure the Hubble constant from these data. So what I'm going to do is I'm going to take half a dozen different models and fit them to these data, and then marginalize over everything except the Hubble constant, and so measure the Hubble constant that way. And this technique is completely independent of local calibration. It's also completely independent of the CMB. Even though I'm using BAO data, I'm going to use this whole compilation of data to actually measure the sound horizon at drag epoch by parameterizing everything in terms of omega b and omega c, and then computing the sound horizon from the model I'm looking at. And so the data I'm going to use are BAO data that go to a redshift of about 2.3, Hubble parameter data that go to a redshift of 1.9, the Pantheon Plus type 1a supernova data that goes to a redshift of 2.3, some quasar angular size data as a function of redshift that goes to a redshift of 2.7, some reverberation measured mapped quasar data with MG2 lines that go to 1.9, redshift of 1.9, and C4 that go to a redshift of 3.4, and Amati correlated GRB data that goes to a redshift of 8.2. And you can see what we get for the Hubble constant. It's between 68.9 and 69.5. And the error bars in each of these models are plus minus 2.4. And so we can say the scatter between 68.9 and 69.5 is a systematic error. So ascribe that to be plus minus 0.3. And then take the central two values and average them and call that the central value. So as a very qualitative summary of all of this is 69.25 plus or minus 2.4. And this, these things don't change as you change the model, so it's giving you, at least within these error bars, almost model-independent measurement of the Hubble constant, which is quite consistent with the median statistics one. It's also quite consistent with Wendy Friedman's group using tip of the red giant branch, measurements from both JWST and the Hubble Space Telescope, and then type 1a supernovae. It's somewhere between about 1.5 sigma lower than Adam Rees's group's measurement that's based on Cepheids and type 1a supernovae. And it's consistent also, but it's our value is about 0.9 sigma higher than the CMB Planck one. And I mean, there is an issue even at low redshift. So there's other measurements at low redshift that are even more spread out than the 73 and 70. So I don't think the low redshift measurements of the Hubble constant have quite been pinned down now. But if the Rees group has the best data, then we do have a really serious problem between the CMB and the supernovae and Cepheids. If this one has best data, current data, then there's not that much of a problem between the CMB and local calibrators. And independent CMB experiments give you results consistent with the Planck. So the CMB data is probably okay. And the only issue there is whether it's model dependent. And so far, they haven't found convincing models that can explain this. So the next thing I want to talk about is space curvature. And So Planck 2018 does not require zero space curvature. It actually favors a mildly closed geometry. But when you start combining it with other data, it gives you flat geometry. If you're looking at ΛCDM with curvature, but possibly things change when you look at dynamical dark energy or in phi-CDM or an XCDM. And maybe the constraints change when you look at non-flat models with time-dependent dark energy. And so I want to look at that a little bit. So we'll first start with the non-CMB data and extend our dynamical dark energy models by putting in space curvature. So now you're going to get 3 free parameters instead of 2. And we'll do that with the phi-CDM model also. So you get 3 free parameters. And I'll spare you the contour plots, just tell you qualitatively what the conclusions are. So we'll use the same compilation of data. And while we were constructing this data compilation, we looked at other low redshift data, and we compared constraints from each of these data sets individually and made sure that they were mutually consistent before we combined them. And we found problems with a lot of other data sets. So there's X-ray UV correlated quasars, which people have been using for the last decade or so. And it turns out those are not standard candles. And reverberation measured H-beta quasars are also not standard candles. And H2 starburst galaxies are also not standard candles. And a lot of people have used these for a number of years to constrain cosmological parameters. But when we use these mutually consistent data sets, we can measure space curvature. And it's consistent with flat geometry for all of those 3 models with non-zero space curvature. And it deviates only by about, at the most, 1.2 sigma. But when we do the same thing with dark energy, we find dark energy dynamics is favored by about 2 sigma. So there's a little more evidence for dark energy dynamics, but you can't really say anything with 2 sigma. So I want to look at these quasars a little bit because this might be pretty interesting. So what we're looking at are AGNs, and you have a black hole here and an accretion disk in the broadline region with the torus there. And so you can measure, if you can measure emission from the black hole and compare it to the emission from here, you can see changes, and those changes, when you correlate them, they can tell you the size of this region. And it turns out the time delay, the time lag, or the size, the linear size, because you can multiply that by c and get the linear size, is correlated pretty well with the absolute luminosity for these systems. And there's a pretty strong correlation here. This is for the MG2 things, and it's about 90 such systems. And so we found this for both MG2 and C4. And the hope is that Rubin will get 10 to the 4 or 10 to the 5 such quasars, some of them going up to a redshift of 4. And if this correlation holds with the Rubin data, this could be another useful constraint on cosmology. So I want to now use CMB data to constrain curvature. And that's much more tricky because we have an extra length scale here, which is set by space curvature. If space curvature is 0, the only length scale around is the Hubble length. And when you have the Hubble length, you can use the Harrison-Peebles use Eldovich power spectrum, the k to the n power spectrum, because there's only one length scale, and the simplest thing you can write down that's dimensionless is that k combined with the appropriate length scale, and write it as a power k to the n. But if you want to include space curvature, you have to use open and closed inflation models to compute the power spectrum. So when Planck did the analysis, they did not use these power spectra, and I'll come to that in more detail in a second. So in the spatially flat case, it's not unreasonable to use this spectrum, and it's what you get from the simplest inflation models. But if you think about a closed geometry, the eigenfunctions of the Laplacian are very different, and they're discrete eigenvalues. That's the eigenvalue of the Laplacian, and those are the capital A, it goes 2, 3, 4, and so on. And sometimes it's more convenient to talk in terms of Q, which is A plus 1. And if you have very, very slow roll inflation, which is something we looked at in the early 90s, you can compute a power spectrum, and it looks pretty messy compared to this, but it's consistent with quantum mechanics and inflation. But it doesn't have tilt because it's very, very slow roll. And so Planck, what they did is they wanted to introduce tilt, so they took this spectrum and multiplied it by k to the n minus 1, and that's how they put in tilt. And they didn't get this spectrum from an inflation model, but very recently I've been working with Alan Guth and Mohammed Hussein Namju, trying to make inflation potential energy densities that give us a power spectrum that's close to this. And we can get them numerically at least. Analytically, it's pretty messy. But we want to use these power spectra to analyze the data. And I also looked at a new inflation model that's non-flat and that's not slow rolling. And that gives me a new power spectrum, which is pretty messy analytically. But you can kind of see what these look like. So if you're looking at the open models, this is the power spectrum as a function of wave number. The blue one is the best fit flat model to Planck data. The green one, okay, we'll forget about the green one for now. So the dotted one is what Planck used in the analysis, and that's kind of indistinguishable up here, and then it comes in a lot stronger at larger multiples or larger wave numbers. And the red one is this power spectrum, and that does the same thing. And the data here is restricted by cosmic variance, so the error bars aren't strong enough to really tell the difference. But when you do it over the whole range, you can tell the difference. And so I want to analyze these models. And things now get messy very fast, and maybe if there are questions, we can go over them later. So again, I'm not going to use DESI data in the next 4 or 5 transparencies. I'm going to use Planck 18 data, so TTT, EE, and low E. And I'll also use the Planck CMB lensing power spectrum data. And for my non-CMB data, I'm going to use 16 BAO measurements, and these include 4 growth factor measurements, and then 9 growth factor measurements from velocity measurements, and then 1590 Pantheon plus supernovae measurements, and 32 Hubble parameter measurements. And I'm going to show you results for 12 different cosmological models, sorry. So 6 lambda CDM and 6 WCDM models. So there are 3 different power spectra. There's the flat models with k to the n, the non-flat models, the Planck power spectrum, and the non-flat model with the power spectrum I computed. And then because there's a degeneracy between this issue of excess lensing in the Planck data, we need to do a consistency check, and that adds in the gravitational potential, the theoretical, the measured power spectrum, and parameterizes it with this parameter A sub L. And the hope is that when you analyze it with A sub L allowed to vary, that you'll come back with A sub L equal to 1, and that doesn't happen. But this is not a physical model that explains what's happening with the Planck data. It's just a consistency check. So I'll start out with the lambda CDM model, and I'll set A sub L equal to 1. And then I want to first compare the consistency between different data sets by, so I'm going to use DIC, that's the deviance information criterion, and turn that into a suspiciousness, and then see whether these data sets are consistent or not. And my threshold is if things don't agree to better than 3 sigma, then they're inconsistent. So for the flat model with the standard lambda CDM, they're very consistent with each other. But for the non-flat ones, the P18 without the lensing data, is about 2.5 sigma away from the non-CMB data constraints. And if you include the lensing data from the CMB, then it's only 1.5 sigma. So my 3 sigma threshold is met. So I can jointly analyze all these data together, and then I can measure space curvature. And I get these really tight constraints on space curvature. It's only about 0.5 sigma away from completely flat. And it's actually giving you open geometry, not closed. So I'm pretty happy to conclude from this that the flat model is really consistent with these data sets. So if I now allow A sub L to vary and look at these constraints again and just compare these guys, they're much more consistent with each other. And now I can look at omega curvature again, and the consistency with flat increases, so it's only about 1/4 sigma away from flat, and again it's favoring open. But A sub L starts deviating from unity by about 2.5 sigma. So I think lambda CDM and these data sets that I used, the BAOs, supernovae, Hubble parameter, and the growth factor, are consistent with flat geometry, but these data seem to want more lensing than is predicted by the best fit lambda CDM model. And it's unclear whether this is a problem with CMB data. So ACT and SPT don't have this problem, but their error bars are significantly bigger than Planck. And there's also a new reduction of Planck data that's called PR4 that does not favor as big a deviation from unity for A sub L. So we're still running that with these other data sets, and we don't have results now. But if you look at XCDM and set A sub L to unity, then there's huge deviations between the constraints from CMB and non-CMB. And what's happening is that CMB data wants to push this model into the phantom region, and it wants omega to be much less, so significantly less than -1. And non-CMB data wants it to be in the quintessence region, and it wants it to be bigger than -1. And it wants, so these guys are inconsistent at my 3 sigma threshold, so this model doesn't work if A sub L is unity. If you allow A sub L to vary and determine it, then the inconsistency reduces to below 3 sigma, and then I can jointly analyze these data sets. And if I jointly analyze all of them together, I again get non-flat geometry that's almost consistent with flat geometry. It deviates by about 3/4 sigma, and I get about 1.5 sigma deviation that's favoring dark energy dynamics, and it's quintessence-like. It's bigger than -1. And again, A sub L wants to be about 2.5 sigma, 3 sigma bigger than unity. So the last couple of slides are the DESI results. And I'm not going to use any of the DESI data. I'm going to use the same data compilation I have and look at the omega naught, omega lambda model where they parameterize the equation of state this way. And you can see that if z is close to 0, this term goes away. And at low redshift, it's an XCDM or WCDM model with omega naught being the equation of state parameter. And at very high redshift, where the CMB is important, this term becomes unity. The z divided by 1 plus z is unity. So it becomes an omega CDM model again with a different equation of state parameter. And lambda CDM is at omega naught equal to -1, omega A equal to 0. And when we compare these two different data sets, they are not inconsistent anymore. They're not as bad as these results here. So we can do a joint analysis. And from the joint analysis, this is what we get. At low redshifts, it favors quintessence, where the non-CMB data dominates. And at higher redshift, it favors quintessence, phantom-like dark energy, the equation of state parameters less than -1. And they're both about 2 sigma, 2.5 sigma away from lambda CDM. And these constraints from our data compilation were stronger than the DESI first year, the 2024 results, but they're completely consistent with them. And you can see what's happening over here. So lambda CDM would be where these two lines intersect right over there. And this is the CMB data, and it's over on the phantom side. And the non-CMB data is over on the quintessence side. And when you jointly combine them, you get the blue contours. And if you zoom in, you can see the 2 sigma blue contour just touches that lambda CDM point. So these data favor dynamical dark energy that's 2 sigma away from lambda CDM. There's two interesting things about our analysis. So our analysis did not use the DESI data. So this 2 sigma favoring of dynamical dark energy is completely independent of the DESI results. We also redid the analysis, throwing away the supernovae data. And that's the dominant, that and the BAO are the dominant pieces in the non-CMB. And the 2 sigma result stays the same. So if anything's happening, it's coming somehow from the CMB data. So the next thing we did is we added in this A sub L parameter and did the same analysis again, but with A sub L in there. And we find that the evidence for dark energy dynamics is reduced down from what we had before. Previously, this was 2.2 sigma away. And the contours now that are relevant are the 1 sigma ones. If you look at this really carefully, you can see the cross is just outside the darker blue contour. And you can go to this on archive and zoom in and see that. So A sub L then goes back to being about 2.5 or 2.25 sigma bigger than unity. And somehow that seems to be suggesting that this evidence for dark energy dynamics in this parameterization, which is not a physical parameterization, is partially caused by the excess smoothing of the Planck PR3 data. And okay, so the other issue about that is that that's not a physical model. And if you use the phi CDM model, and we've just done this with the 2015 data, we haven't finished our 2018 analysis. It's slightly better fit than the lambda CDM model, but not by any significance. And we're trying to finish up our 2018 Planck analysis of the phi CDM model. So I think these are the really important questions right now, at least in the short term. We don't know much about dark energy. We don't know whether the universe is closed for sure. It probably is flat. And we don't know whether this A sub L evidence from these data is a problem, whether it's a problem for the standard lambda CDM model, it's a problem for the data. And we don't know what the dark matter is. So the red things are what I think are true, that dark energy dynamics is still allowed, and it's probably flat, but it's kind of really useful to try to better understand these non-flat inflation models, at least from a theorist's perspective. And I hope BAO data from DESI and Euclid will help resolve these issues very soon. And maybe we'll get something from the LHC or these deep underground experiments for dark matter. And once you've solved these problems in your theses, don't worry about whether cosmology is going to be over. So I'll leave that up for a few minutes, a few seconds. Thank you very much. Thank you. There's half a question here.
So you highlighted that the combination, including previous BAO results, are consistent with although with small error bars, the DESI hard to fold in the DESI results just simply? You have to do a joint analysis?
Yeah, because a lot of the weight in the previous one's flown, and they're covering part of the same region as.
In your mind, just
No, yeah. So we'll at some point we'll wait a little bit and then just transition to DESI.
but you're waiting for DESI 3, year 3.
Yeah, because that, I mean, so from their papers, that has more weight than what we had. So we're slightly heavier than DESI 1, the 2024 paper. So hopefully, by the time they get to 5 years, they'll have much better data and they'll have a much better understanding of the data.
This is the time to ask a question you always wanted to ask, but was scared.
Can I ask you another question?
So when it comes to the LOA data and this like dark energy, do you have any sense or motivation behind like if that is true, how we should be thinking about it?
So I didn't get the first part.
Like in terms of like LOA and like the DESI results,
Yeah, okay.
you have like this phantom energy,
Yeah,
right?
yeah.
State. Do you have any personal sense as to like how to motivate that or think about that?
It seems really difficult to get that kind of behavior in a field theory, a scalar field theory, a simple one. I mean, you could probably try 2 or 3 scalar fields and see if you can come up with something. But it would be nice to try to understand what's causing the W not ΛCDM result, and whether it's anything to do with Planck data set. And we're doing the PR4 analysis now, and hopefully in 2 or 3 months that'll be finished, and we'll know whether it's in that one too. And if it's there, then we got to think about something else, another explanation. But omega naught omega ΛCDM is not a physical model, and it's got the same problem. If you take dp rho, it's negative, and the speed of sound is squared is negative, and speed of sound is imaginary. And if you just think in terms of Jeans instability, as e to the I omega t's will be e to the plus omega t, e to the minus omega t, and one of them is going to grow exponentially fast.
See if there's any other questions. Can I ask, can you put a cautionary tale? So I was scared a little bit about the 10 to the 4 reverberation measurements, because then you will discover so many quasars, but then actually getting the time delays that you need
Yeah,
is tricky.
yeah, that might be a lot of work.
Rubin is going to be hard.
Yeah,
You need another telescope
yeah,
to follow 10,000 objects.
yeah,
That's scary.
yeah, yeah. So I mean, even if you get 1,000 instead of 10,000, yeah, because that's a factor of 10 or more than what we have now, and it's going to be it's one instrument if Rubin can do it, and these other things are multiple instruments.
This A sub L parameter, the lensing parameter, what are you like thinking this represents physically?
It's a consistency test. It's not a real physical model, and you kind of hope that it comes back to unity with error bars that are consistent with unity, and it's not doing that. So it's telling you that it's failing this consistency check, and maybe 2.5 sigma is just a statistical fluctuation, and maybe Simons with a lot more data will get tighter error bars than ACT and SPT. Because ACT and SPT now have bigger error bars, and they're consistent with A sub L equal to unity. And PR4 in just lambda CDM, it's only 3/4 of a sigma away. But we seem to be finding a little bit bigger deviation when we use our data in that analysis, but we haven't finished it.
If there's not a last question, I will ask. Oh, Max.
One of the questions raised on one of your previous slides was we need to better understand inflation in non-spatially flat background